Okay, we're getting down near the end of the course, but we're going to cover some really important topics in Unit 16. So starting with 16.1, this is basically an introduction to what we're going to be studying in the entire unit. So the I can statement for 16.1 is I can recognize and name the basic shapes of conic sections. So let's write the word conic right here. And we'll talk about conic sections in just a second. We're going to use the distance formula to find the distance between -2, 5 and xy. So a little bit unusual that we've got this point where we don't know what the numeric values are of the two coordinates. So we're going to set up the distance formula. The distance formula is a big square root, and then we're going to do x2 minus x1. So this is x2 minus 2, and we're going to square that quantity. And then y2 minus y1, so that's going to be y minus 5 quantity squared. So if I were going to simplify this just a little bit, I'd write x plus 2 quantity squared plus y minus 5 quantity squared. Make sure that's underneath the square root. And that would be the distance between the two of those. So I'm just going to go ahead and circle this right here. There's our answer for the warm-up. And then we've got this diagram down below. So let's talk about what the conic sections are. There are actually 4 conic sections. They are a circle, an ellipse, and then a parabola, and what's called a hyperbola. Okay? So they're called conic sections because they are literally slices, or in other words, sections of cones. And it happens to be a double cone, so it looks like this. So it's a cone with an inverted cone on top of it. So here's what happens. We're talking about taking a plane and slicing it across that cone right here. And if we slice it perpendicular to the axis that runs right down the center of the two cones, then we get a circular shape right here. So if we diagram this down below, so it looks kind of like an oval from the side here, but looking at it from straight above, you can imagine that it looks like a circle. If we tilt the plane just a little bit, it kind of elongates that circular shape and we get what's called an ellipse. And then if we tilt it even just a little bit more, this section, this slice that it curves out, comes out in the shape of a parabola, and we've actually studied those before. A really interesting one is the hyperbola. So on a hyperbola, we've got this plane that's slicing this cone, this double cone, and because it's more parallel with the axis of the two cones, it actually makes a branch on the top and a branch on the bottom. And I want you to take a look at these. So we'll look at these a little bit more in depth in just a second, but we've got a circle right here, we've got an ellipse, we've got a parabola, nice curve shape here that we've talked about before, and then we've got the hyperbola. And what I want you to notice is the really subtle difference between the shape of the parabola and each one of the branches of the hyperbola. They kind of look similar, but they're definitely different. What happens here is on the parabola, these sides, these ends continue to go up and out, and they continue to curve up and out, and they get steeper. While on the branches of the hyperbola, what happens is they get really, really straight. So this one would just kind of straighten out like that, and this one would straighten out like that. So each branch approaches a straight line. So approaches a straight line right there. Now we can actually demonstrate how conic sections are formed. A quick little demonstration using a flashlight. I'm actually going to show this in class. If you're in class, so I'll actually be physically using a flashlight. I'm going to go ahead and play this video right now so you can see how those conic sections are formed and maybe have a little bit better visual than just having a two-dimensional thing right here. So let's go ahead and take a look at that. Here's an easy way to visualize and model how conic sections are formed by slicing a cone. We've probably all seen a cartoon character with a flashlight in a dark room. It kind of looks like a cone of light. If we look at it from the side, the cone looks like a two-dimensional triangle. But since it's three-dimensional, it really is a cone. If the flashlight is pointed straight toward us, the flashlight looks like a small circle. And the cone of light looks like a big circle. Keep this three-dimensional cone of light in mind. It will help us visualize the shapes as we slice a cone and form all 4 conic sections. If we point the light straight toward the wall, we see a circle. If we angle it just a little bit, it stretches out the circle and makes an ellipse. If we angle it even more, one side of the cone stops intersecting with the board and we get a parabola. Finally, if we point the light so it's parallel with the board, we get one branch of a hyperbola. Notice how the shape curves near the source of the light and gets really straight out near the ends, kind of like the triangle. We can go back and forth, and we can see the shapes appear and disappear as we change the angle. from perpendicular to the board with the circle to parallel to the board with a hyperbola. All right, so that's all well and good, and that's kind of interesting and a fascinating demonstration, but what are they good for? Where do we use conic sections? Well, they're used a lot in astronomy, satellite transmissions, optics, projectile motion, which we've talked a little bit about before, radar, navigation, and there are really a lot of different applications of conic sections. You might find this short little video kind of interesting. It introduces conic sections, shows some different modeling for each one of those, and then shows some of their uses. There are some conic sections that are some shapes that people think are conic sections that are not. They're actually shown in this video, but you get the general gist. I think it's about a 3 or 4 minute video, so you're welcome to watch that now. And then just a point here, each conic section has a definition that produces the equation, and that's going to be the interesting thing about what we do. It's going to produce an equation, and therefore, once we have the equation, it's going to produce the shape of that. And as we mentioned in the warm-up, the definitions for conic sections use distance a whole bunch in order to derive those equations. So when we see the equations on the next page, you'll see what I'm talking about. There are a ton of similarities in the equations. They're kind of hard to keep straight which is which and stuff like that because all of the equations have perfect squares in them, which if you think about it, if we come back up here to the distance formula, look at those perfect squares in there. So we're going to have perfect squares and squared terms in the equations. So anything, we've got x squared, y squared, quantity squared, we're going to have a quantity squared, a binomial squared over a constant and stuff like that. Whole bunch of things, and they'll all kind of look similar, but we'll try and make sense of which is which. Okay, we're on the back side, and I've got a model or a quick diagram, quick graph of each one of these. So we've got the parabola, the circle, the ellipse, and the hyperbola. And just for simplicity, I centered each one of these at the origin. And you'll notice that only one of these is a function. So a function has to pass the vertical line test. This first one is the only one that's a function. So these equations right here would all produce parabolas. And these equations right here, they would all produce circles. These equations down here would all produce ellipses, and these equations over here would all produce hyperbolas. And it's really easy to get mixed up and say, well, my gosh, they all look basically the same. But if you look really closely, you'll notice a couple things about them. So I want to focus on this one right here, this one right here, this one right here, and this one right here. So I diagrammed these and wrote these down so they could kind of illustrate this point. So we've got the parabola up here, we've got the circle right here, the ellipse right here, and then the hyperbola down here. So if they're set equal to 0, or basically if we have them in what we call general form, have the variables on one side of an equation, it's really pretty easy to tell. So if the equation has one squared variable, so the only one that only has one squared variable is a parabola. So that's the easiest one to pick out by just looking at the equation. If it's got one squared variable, then it's got to be a parabola. The rest of these, they all have two squared variables, but if you look at them, we can still tell them apart. If they have the same sign and the same coefficient, so that's this one right here, they have the same sign, they're both positive, they both have a 1 in front there. If they have the same sign and the same coefficient, then it's a circle. Okay, oops, I was going to write coefficient there, circle here. Okay, if they have the same sign but they have different coefficients, then it's going to be an ellipse. And then the only other one that's left here is a hyperbola, and let's see if we can tell what's going on here. So again, all three of these have two squared variables, but if you take a look here, as long as they have different signs, it's okay if they have different coefficients, but as long as one's positive and one's negative, then it's got to be a hyperbola. Okay, so we're going to write different right here. Different signs, then it's a hyperbola. Hyperbola. Okay, and my penmanship's horrible here. We'll try and make that look a little bit better. So we're going to come down near the bottom here, and we're going to see if we can figure out what's going on with this. Again, there's not really a homework assignment for this particular section. All we're interested in you doing is just becoming familiar with the equations and that sort of thing. So all we need to know is if there's one squared variable, it's got to be a parabola. Okay, so it's got to be shaped like this. Whoops, not quite like that. There we go. If it's got two squared variables, then it's got to be either a circle, ellipse, or hyperbola, and here's how we tell. If they have the same sign and the same coefficient, it's going to be a circle. If they have the same sign but different coefficients, so different numeric coefficient out in front, then it's going to be an ellipse. And if they have different signs, it's going to be hyperbola. So let's take a look at this one. Let's see, there's one squared variable here. It's only got one squared variable, so that's a parabola. Okay, so there's 4 examples here, so we're probably going to get one of each. If we take a look at this one, this has 2 squared variables. And this one, they're both positive, but this one is a 5. So they have the same sign and different coefficients. So this one's going to be an ellipse. And this one right here. Now notice that this looks a little bit weird. The coefficient here would be 1/4 and the coefficient here would be 1/16. They're different coefficients, but that's not what matters here. What matters here is that this one is negative and the sign on this one's positive. So that's going to be a hyperbola. Hyperbola. And then the last one here, it's got to be a circle, you would think. Same sign, same coefficient, same sign. They're both positive, same coefficient. They're both +1. So this is going to be a circle. Okay. Now, the only other thing that I want to mention here is there are often times where people will see shapes in nature, or they'll see them in, on signs or different things like that. And they'll say, oh, that's a parabola, or that's an ellipse, or that's a hyperbola, or something like that. You have to be a little bit careful. What I've got right here is a picture of the St. Louis Arch. It's also called the Jefferson National Expansion Memorial. If you ever go there, it's really cool. Highly recommend that. A lot of people will look at this and they'll say, oh, that's a parabola. It's actually not a parabola. It's actually what's called an inverted catenary. And a catenary is what you get if you take a weighted chain. So imagine just a steel chain and you hold it on both ends. So you hold one end here and one end here. It tends to be a little bit steeper and then a little bit flatter in between. Looks a heck of a lot like a parabola, but it's not. Okay, so just keep that in mind. And then the I can for today is just I can recognize and name the basic shapes of conic section. That's it. No homework as long as you're familiar with the names and the shapes. All right.